Good morning, everyone, and welcome to today's installment in the Sustainable Brands BootCamp series, Introduction to Lifecycle Impact Assessment, produced by Sustainable Life Media and sponsored by Dell. Our speaker today is Jeremy Faludi, a lecturer of green design at Stanford University and research lead at Project Frog. Jeremy will be talking with us about life cycle assessments and providing us with tools and approaches with which we can better utilize this framework. As usual, there's just a little bit of housekeeping to take care of before we get started. Our session will be 90 minutes long today as usual, and that will include the Q&A portion at the end of the program, which will begin in approximately 1 hour. If you'd like to ask a question during the presentation, you can type it into the field titled Ask Jeremy a Question, located directly below the PowerPoint window in the center of your screen. You can submit written questions and comments at any time during the presentation, and I would encourage everyone to do so as things come to your mind as the presentation progresses, as it will help us frame the Q&A after. You'll also notice you have a button that reads full screen sitting right on top of your PowerPoint deck. If you need a closer look at the slides, you can just hit that to full screen the PowerPoint deck, and you can push it a second time to return to the full webinar screen. Now, it's my pleasure today to introduce Jeremy Faludi. Jeremy is a sustainable design strategist and researcher, lecturing on green design at Stanford University and designing modular green building systems at Project Frog. In the past, he's worked with the Rocky Mountain Institute, the Biomimicry Institute, and the Lawrence Berkeley National Labs. His work has appeared in the Wall Street Journal, San Francisco Chronicle, Treehugger, CNET, and Sustainable Industries Journal. Jeremy, thanks so much for taking the time to be with us today.
All right, thanks for having me. So we're going to talk about life cycle assessment or life cycle analysis. The people who are actually practitioners in the field tend to call it life cycle assessment these days, but either way is fine. And so the first question is, what is this good for? Basically, the goal of life cycle assessment is to capture and quantify all of the environmental impacts of your product or your service or whatever it is that you're trying to analyze. The trouble with that is it's kind of impossible because we don't even know all of the impacts of everything that we're doing. For instance, we don't know all of the toxicity implications of the air pollution giving off from, let's say, steel foundries when they're forging steel, or all of the impacts of, say, some of the solvents that we use for adhesives or paints. But it's the best tool that we've got right now, and a lot of people are somewhat skeptical of LCA sometimes because it can't capture all of the impacts, or there are different ways of thinking about how you weigh one thing against another. But it's kind of like physics in the 1700s. It's a total mess, but it's better than anything else out there, which is mostly guesswork and superstition. Now, if you're a long-time expert in sustainability, then you probably do have a decent intuition about what the biggest impacts or less significant impacts of a product are. But for everybody else, I would say life cycle assessment is a crucial tool and the most credible tool that we have at our disposal. So the trick is that because you can never have a perfect LCA, you can go down an infinite rabbit hole in terms of how much detail you want to go into, how much time you spend researching things, how many primary sources you go to, because if you're going to just get industry average information on a process, like, say, making steel or making polyethylene or something, that's pretty easy to do. You can just look that up in a database from numbers that other people have researched in the past, but it'll never quite be your data because they didn't go to your factory and measure it. But of course, you going to your own factory and measuring all the air emissions, all the water emissions, all the soil emissions, all the raw materials, etc., is incredibly expensive and time-consuming. And so the question when you are doing LCA is, what are you doing it for? Because that is really going to determine the degree of depth to which you go, how far down the rabbit hole you want to dive. And so there are a number of things that LCA is commonly used for. These are most of them, and they vary in the degree of precision and depth that you need. So, for instance, the first one, telling the backstory, that you don't really need much detail at all. In fact, you don't necessarily even need numbers for that. You just need to give your clients or your investors or your customers some sense that they know where this product is coming from, what it's like in its use, where it goes at the end of its life, etc. And but the next three, you do really need a certain level of technical rigor for, because you're going to use them to make decisions. So identifying the biggest impacts of your product, you want to know to a certain degree of precision what the biggest impacts are, whether it's the materials you use or the processes that you use to form them, like with steel. Are you stamping the steel? Are you forging the steel? Are you machining it, etc.? Components, pre-bought assemblies that you're getting from suppliers, other systems, and when you're identifying the biggest impacts, what you're trying to do is make intelligent decisions about the product to say, okay, well, this is the biggest impact, so we should eliminate that or find a replacement for that or somehow find a way to do that better. So that's important to have good data for that. Establishing a baseline for improvement is very similar. So if you want to develop a company policy where you say, we want to cut our environmental impacts in half in the next 5 years, let's say, well, you need to know where you are now in order to know when you get to halfway reduction. And likewise, you need to know what's reasonable, what's possible for you to do. And likewise for guiding product development and process development, again, that's going to be a matter of finding what your biggest impacts are, as well as looking at alternatives, different scenarios, and seeing what the impacts of those are, how they compare, establishing the baselines, and doing other scenarios for what might be possible. So those three are kind of all at the same level. And then the highest level of detail and depth that you need is supporting product certification. And right now there aren't any widely used certifications that require life cycle assessment, but there are some that do exist, and others that are on their way. And so it's going to be a bigger thing as time goes on. And likewise, this brings up the question of, do you trust the analysis that somebody else did? And it's some of the important factors are whether they're using product-specific data versus industry average data. Like I said, did they just look up a number in a database somewhere, and did they take the right number from the right database? Were they looking at, say, European average data when the product is in fact made in the US or made in China, let's say? And whether it's prepared by an experienced practitioner, because LCA does have a lot of subtleties to it, and to do it requires a lot of assumptions. Inherently, you have to make assumptions at various points along the way, and an experienced practitioner will make more intelligent ones than someone who's new at it. A big factor in whether you trust the analysis is whether it was done to certain industry standards. There is an international standard, ISO 14040, and that's basically the bar by which a credible LCA is measured. And there's an emerging standard that Scientific Certification Systems here in the US is trying to develop, and that's SCS 002. And of course, the best level for credibility is whether the analysis has been verified by a third party, like Scientific Certification Systems or another professional organization that's very good at this stuff. So to give more detail on different scenarios that you might be using LCA for, this is an example of telling the background story. It's some informational print on a chocolate wrapper developed by this designer, Arlene Birt, and it basically tells the story of where your chocolate comes from. If you, I'm going to use the pointer here. So at the beginning, it tells you where the coffee came from, and tells you that it was organic and fair trade. Then it tells you how many miles it traveled to go to the factory. Once in the factory, tells you the other ingredients, and tells you how far it traveled again to the supermarket, and then gives you a little bit of info on the company, basically. So not much detail, very few numbers, but just gives the customer more of a sense that they know where this product is coming from. And I think the best book that I've seen on telling the stories of products is called Stuff, The Secret Lives of Everyday Things, by a company that used to be called Northwest Environment Watch, is now called Sightline Institute. They're a nonprofit up in Pacific Northwest. And this is a great book because it basically gives you a life cycle analysis of 5 or 6 different everyday things: a cup of coffee, a t-shirt, a car, a bicycle, a computer, and I think a hamburger. But it does it not in a dry academic way, but in a narrative kind of way where it's telling you the story of each of these products. It's a bit dated now because it's 10 or gosh, almost 15 years old, but I still have yet to see a better book out there. And so that's telling the background story, identifying the biggest impacts. This is going to be a fairly typical graph that you would see upon doing a life cycle assessment of something. Don't worry about the different colors in the bars for now, but basically all the different bars are different components in the manufacturing of a product. In this particular case, this is a hairdryer that I did an analysis for a company a couple of years ago. And as you can see, basically 3 of the components are by far the biggest impacts. And so if you're trying to make decisions about product development or process development, then those are your 3 biggest targets. And the units of measure that are used for this scale are what's called millipoints. And that's a made-up number, basically. Remember, this is kind of physics in the 1700s here. But so what it is in this particular methodology, there are different methodologies which we'll get to in a second. But in this particular methodology, 1 point is 1/1000th of an average European's annual environmental impact. Okay, so kind of a meaningless number on the face of it, except that as long as you use that same scale for everything, you can use that same scale to measure these different components of the hairdryer against each other, and you can use them to measure this hairdryer against your television or your couch or your commute to work in the morning. As long as you use the same scale, it does have meaning in relative terms, just not necessarily in absolute terms. So it ends up being a very useful thing, and each methodology has their different way of determining what a point is. So this is that same hairdryer, but all of the bars from the previous screen are wrapped up in here. So this is all of the manufacturing of that hairdryer. And then this is the transportation from from China to an average home in the US, basically. And then this bar over here is the electricity used during the life of the hairdryer. So if you were looking back and trying to see, okay, what are the biggest impacts, what are our top priorities for changing the design of this hairdryer, you might think that it was this or this, but in fact, those are still both irrelevant compared to the electricity used during the product's life. And so that would really be the top priority. And for establishing baselines, these are different kinds of packaging for that same client that I analyzed. And this one here is, sorry, that didn't take the arrow. There we go. This one here is the packaging that they use today. And I ran a couple scenarios on how could you improve that. And so this is basically a clear PVC blister pack. And I said, well, what if you do the same thing but using corrugated cardboard, and then you get this? Or what if you do the same thing using cardstock, like a cereal box, then you get this. And so it's clear that through a simple material substitution, you can cut the environmental impact of the packaging by 2/3, just like that. And so if you're trying to guide product development or establish baselines, you can say, wow, we can make a 66% improvement overnight here. So that's not actually a very ambitious goal. So what if we try to improve by 90%? And so we're talking about these impacts and points and bar graphs and stuff like that, but what are we actually measuring? The answer is basically different depending on what methodology you're using, and there are a lot of different methodologies. So, for instance, here's a list of some of the most popular ones. Eco-indicator is probably the most commonly used for the product world, although not for the building world, at least not in the US. That the methodology most commonly used for that is called BEES. But for products, it's eco-indicator. This is a methodology developed by a company called PRE in the Netherlands. But in the US, the EPA has a standard called TRACY that is sort of the most standard here in the US, even though a lot of people, if not most, still actually use eco-indicator. But some very good reputable companies do use TRACY. For instance, the Ocala Guide and Sustainable Minds use TRACY points. They rebrand them as Ocala points, but they're TRACY points. And there's a few other ones here. One interesting one is Economic Input-Output, LCA. That's by Carnegie Mellon. And that one is a different approach than most of these. Most of these will give you the ecological impact per unit mass or per unit weight of the of whatever items you're measuring, whether it be plastic or steel or batteries, etc., etc. But Economic Input-Output, LCA, instead measures things, ecological impacts per unit dollar, per economic value of the system. And I don't like that as well myself, just because I feel like it's a little less real. Prices change all the time. But some people do like that, particularly some business folks, as you might expect. So with the Tracy system, which is again by the US EPA, here are all the things that it measures. So in resource depletion, it measures the use of fossil fuels, but that's all. It doesn't measure, say, the mineral depletion or water use. In ecosystem health, it measures climate change, acid rain, ecotoxicity. Now, if you've never heard of ecotoxicity, that is basically being toxic to other plants and animals, but not being toxic to humans. And then water eutrophication, if you haven't heard of that, basically that's when rivers or streams or lakes get too many nutrients in them. And you might say, how can you have too many nutrients? Nutrients are a good thing, right? Well, the trouble is, if you get too many nutrients, basically mostly nitrogen and phosphorus, then you can have blooms of algae in the lake or stream or whatever, and that can either shut out the light to other plants, or you can get a big bloom of algae and then it dies off, and that sucks out a lot of the oxygen from the water, and then can basically asphyxiate fish. So that's what eutrophication is, and then ionizing radiation, that's what people mean when they say something's radioactive, and stratospheric ozone, habitat destruction. And then in human health, Tracy measures carcinogens and human toxicity, sort of all lumped together as one thing, and smog and particulates. Now, the eco-indicator system measures mostly the same things, although it sort of categorizes them differently. But there are a couple differences. For instance, in resource depletion, it does measure mineral depletion. Still does not measure water use, which you could certainly criticize them for, although in their defense, and in Tracy's defense, the degree to which water use is important as an impact varies very widely depending on where it's used. So using water in the Pacific Northwest, not a big deal. There's tons of water around. It rains all the time. Whereas using water in Las Vegas or Phoenix, Arizona or something like that, very big deal. And so just to avoid the whole problems of normalizing that, they just kind of ignored the problem. But we'll see how these things change in the future. And so then ecosystem quality, again, it's mostly the same things, although they've broken it out a little bit differently. Instead of acid rain, they have water acidification. And instead of habitat destruction, they have land use, which includes both habitat destruction and the use of some bulk resources like sand and gravel. And then in human health, they separate out carcinogens from a couple different kind of air pollution, respiratory organics and inorganics, basically whether they're carbon-containing molecules or not, and they've still got climate change and ozone depletion and radioactivity. And then there are other methodologies like the IPCC's that only measures greenhouse gas emissions. So all those greenhouse calculators that you'll see online, they're all doing crude life cycle analyses, but the only thing that they're measuring is climate change. And so here is a graph of some of the impacts of that hairdryer that I showed earlier, but instead of showing the impacts by component, it's showing the impacts by the kind of impact. So this is, I apologize for the small print, but In fact, I'm even having a hard time reading this, so I'm going to full screen it. So this one here is carcinogens, respiratory organics, respiratory inorganics, climate change, radiation, ozone layer depletion, ecotoxicity, acidification and eutrophication, land use, mineral depletion, and fossil fuels. And the different colors that you see here, yellow is the electricity use during the hairdryer's life, and red is the manufacturing stage, and green is the transportation from China to the US. And so once again, you can see that that transportation is not very big, and that the overwhelming use is electricity. And you can see that the impacts of electricity are mostly fossil fuel depletion and air pollution, basically. So, okay, so measuring the variables is all very well, but then you also have to compare them. Now, people who are serious academics or very hardcore practitioners of life cycle assessment, they will sometimes say that no, you actually can't compare these different things, because how many units of climate change is worth 1 unit of carcinogens? You know, is 4 points of acidification equal to 6.3 points of ecotoxicity? You know, it's kind of a stupid question. And so some people that are hardcore will say that you just can't do it, except that for us as designers or us as managers or people who are making decisions about a product, we need to make those comparisons, because in the end, we need just a single score of, is this hairdryer model better than that hairdryer model? So that we can choose which one to put on the market and which one to drop. Or we can choose how to change our product development, our process development, etc. So for practical purposes, we really need to compare these things, even though it is comparing apples and oranges. And there are various different methodologies of doing that. Each of the different methodologies that I listed before has their own way of doing that normalization. And so, so again, it's just a matter of which analysis method you prefer, you think is most credible, or is a standard for your industry. So, okay, so that is sort of about the concept of LCA, the theory of LCA. So what's it like to actually do LCA? Well, it's basically these steps. First, you'll determine the system boundaries, and we'll get into more detail about what all these are in a minute. But the boundaries are basically what is counted in your analysis and what is not counted. And determine the product's life and the functional unit. So are you measuring the impacts per year of life of the product? Are you measuring the impacts per hour of use or per incident of use, etc., etc.? And you'll gather all the product data, which again, is all the materials, all the processes that you use, like injection molding or stamping or whatever, the transportation, not just of the materials from their origins to the factory, but then also from the factory to the store, and from the store to the customer's home. And then energy use during the product's life, and what happens at the end of its life. Is it landfilled? Is it incinerated? Is it recycled? Is it reused? Etc. And then you'll compute all of these, and you'll get some bar graphs like we were showing earlier, and then you have to make some sense of that so that you can make decisions. I'm just going to grab a drink of water here. By the way, I haven't seen any questions so far. Feel more than free to ask questions. Although, actually, I just got a question saying, is disposal measured in any of these methods? And the answer is yes, which is basically, so if you look back at these impacts here, disposal will cause things like land use in the form of a landfill, or if the product is incinerated at the end of its life, then that will cause air pollution like respiratory inorganics and organics, and it can cause some climate change as well, depending on what the CO2 impacts of incinerating that product are, etc. So yes, absolutely, disposal is measured in all of these, and it's it's a question of what are the impacts of that particular kind of disposal. And yeah, anybody else that has questions, by all means, pipe up. So, so boundaries. So when you're deciding what is and isn't part of your analysis, I think that this agave is kind of a good metaphor for it, because the closer in you draw your boundaries, the easier it is to be certain that you know what you're talking about, and that your boundaries are well defined, and that your assumptions are well defined and reasonable. The further out you draw your boundaries, the more of the product's impacts you include, but the messier your analysis gets, the more it relies on outside data that you don't know, that you have to make assumptions about or make guesses about. So, for instance, with like with a cell phone, let's say, if you could say that, okay, the boundaries of my analysis are just going to be looking at the manufacturing of this cell phone and the electricity that it uses during its life, but I'm not going to include all of the cell towers that I actually use to communicate. And granted, without the cell towers, this would be totally useless, right? But it becomes such a harder problem at that point to look at all the material use and installation and energy use of all those cell towers and figure out how many cell towers you're using and what percentage of those cell towers' use is due to your individual phone rather than the other millions of customers that use the same system. So you get a more complete analysis, but there are a lot more assumptions, it's much messier, and so there are good arguments for drawing the boundaries further in and saying, we're not going to include that, we're just going to look at the phone itself. Okay, and so determining the product's life and the functional unit is a very simple thing that you do up front. It sounds like it's a very basic, obvious thing, but it's not necessarily. For instance, these two coffee cups here. The one on the left is a paper cup, and so it uses much less material than the ceramic cup, and ceramics require firing in a kiln, whereas paper wood pulp doesn't require that to be made into paper. So it's less energy intensive to make the paper cup, and they stack better in shipping, so you have less transportation impacts. And so the paper cup is clearly the more ecologically friendly choice, right? Well, no, of course, because you're only going to use the paper cup once, whereas the ceramic cup is going to last you hundreds of cups of coffee. So then you should say, okay, well, so the functional unit is not just ecological impact per product, but ecological impact per cup of coffee drunk, let's say. which is great. Except that if you look carefully, the paper cup is actually bigger than the ceramic cup, and so it can hold more coffee. And so to really get a fair measurement, you would want to measure the ecological impact per, let's say, liter of coffee drunk or half liter of coffee drunk, whatever. So that would be a good functional unit. And again, determining the product life, how long does a ceramic mug last? Well, it could last for thousands of years. I mean, we're digging up ceramic vessels from ancient Rome, right? Or you could accidentally drop the mug on the floor and break it the day after you buy it. And so you just have to make an assumption here about how long the product lasts. And that'll make a big impact in your analysis, because if the ceramic mug only lasts one day, then it's a much worse ecological choice than the paper cup. And I see we've got another question here. Let's see, do you think, in addition to ingredients on food, for example, that packaging will also include some type of standard comparison model for LCA impacts? It seems consumers are becoming more savvy and motivated by that more than cost. I think that is an excellent point, and in fact, I really want that to happen. And I actually have created my own theoretical eco-label for the for the World-Changing book. I also write for worldchanging.com and was one of the co-authors of the book World-Changing: A User's Guide to the 21st Century, and put an LCA-based label in that, which has also appeared in a couple other books, Packaging Sustainability by Wendy Jedlichka, Green Graphic Design by Brian Doherty, and eco labels, concerns and experiences by Asha Joshi. So yes, actually, I can't wait until that happens. And I think that having an LCA-based label would be the best, most credible, and most informative labeling system that we could have for products. Absolutely. And we can talk more about that at the end if you want. Okay, so next step is gathering product data. And this sounds fairly simple. It's a little more complicated than you might think, because most manufacturers, they don't actually know all of the data for this stuff. So it'll be one thing to get a bill of materials and then to assign weights to those different components by probably just tearing the product apart and weighing each different component. That's what you often need to do, because most people don't track how much their components weigh. But then the tricky part is when you're buying things from vendors. So let's say you're buying a circuit board or let's say a power supply from a vendor. So they will have their own vendors from which they get the components, the resistors, the capacitors, et cetera, the transformers, et cetera. And they don't necessarily want to tell you who those vendors are, because you might go around them. And so once you have a supply chain that's 6 or 7 vendors deep, it's really impossible to track this stuff. And so at some point you just have to make your best guess about where this stuff came from, how many miles away that other factory was, what materials they used, what kind of capacitors and resistors are being used. Often that's fairly easy to tell, but there are a lot of assumptions in here, even though it seems like it would be a fairly straightforward thing. And then you compute the impacts and compare them, and you can either do this by hand or use various kinds of software to measure it and compute things. And if you're doing it by hand, one easy way is using the Ocala guide, which I recommend as a good primer to green design. And it's just a little pamphlet, basically this thick, that gives you the basics of green design. And then in the back of the pamphlet, it has a whole bunch of tables like this, where if you say your product is, so let's say that this product we were just looking at, let's say that this plastic here, let's say that is polycarbonate. And so you go down the list here and you say, okay, polycarbonate. And so that is 180 Ocala millipoints per pound of plastic, or of polycarbonate. And so you would put down in, let's say, an Excel spreadsheet or whatever, just a list that you're making by hand. You would say, okay, so my product has, let's say, half a pound of polycarb, and so half a pound times 180 points per pound. Okay, so that is 90 Ocala millipoints for that part. And then the process that part used was injection molding. And so you say, okay, so down here in processes, injection molding for most plastics is 11 Ocala millipoints per pound. And so 11 divided by 2, 5.5 millipoints for that particular part. And then you just do that for all the other parts, all the steel, aluminum, copper in the wiring, etc., the printed circuit board, and you just add all that up, and then you add in the transportation, how many miles. Actually, it's usually not just miles or kilometers, it's usually something like ton kilometers, which measures both the distance traveled and the weight that was transported. So you just add all that up, and eventually you get a number. But that's kind of the slow and hard way to do it. The faster and easier and more powerful way of doing it is to use software. And there's a lot of software out there. This is not even a complete list of all the different programs that are out there doing this. The software that I think is the best these days for a serious professional life cycle analysis or life cycle assessment is SEMA Pro by Prey. Again, this is for the product world. In the architecture world, Athena is actually the sort of standard in the U.S. But for products, SEMA Pro is the best. And in addition to making the calculations easier and faster, it also gives you a lot more detail. So like we were seeing before, it doesn't just give you a single score for polycarbonate, let's say. It tells you, it gives you a score for all of the different impact categories for the carcinogens and the climate change and the fossil fuel use and the mineral use, etc., for each of your components, for your polycarbonate, for your injection molding of the polycarbonate, for the transportation, etc., etc. Okay, and we've got a question. What is the fundamental difference between Gabi and SEMA Pro? So that's a good question. Basically, in terms of the analysis that you get, there isn't a difference because both of those programs let you use the same methodologies. So you can do an analysis using the eco-indicator method in SEMA Pro or in Gabi, or you can do an analysis using the Tracy method either in SEMA Pro or in Gabi. It's basically just a difference in features and user interface. Just like you can make a three-dimensional model of a product using SolidWorks software or using Pro Engineer software or using Autodesk Inventor. They all do the same thing. They're just different programs that have different features and different interfaces. I personally have had a much better experience on SEMA Pro than I have with Gabby, just interface-wise. But yeah, so they're just different programs for doing the same thing. Yeah. And actually, if you want really easy user interface, then the web-based programs are actually the way to go. So Greenfly has the prettiest user interface, the easiest user interface of any of these programs that I've seen, pretty much on the entire page. Although I don't like their analysis results, because instead of telling you things like carcinogens and ecotoxicity and stuff like that, they'll just tell you things like water use, which again, the importance of that depends on where you are, or electricity use, which again, the importance of that depends on whether you're using, say, hydropower or coal-fired power, and so I don't feel like I can do much or really make decisions with Greenfly's output, whereas Sustainable Minds still has a great user interface, and does give you the proper Tracy points for, or they call them Ocala points, yeah, they give you the good data at the end that you can really make decisions with. But then Sustainable Minds doesn't have all the features that SEMA Pro would. So SEMA Pro, you can do fancy things like you can do sensitivity analysis in an automated way, and we'll talk about what that is in a minute. You can do Monte Carlo analysis. You can do, basically you can, and Sustainable Minds, it just gives you the results as a single score, like we saw a minute ago, 180 Ocala millipoints, rather than breaking things out into the air pollution and water pollution and toxins and stuff like that. So there are various reasons to use different kinds of software. And one other one worth mentioning is Sustainability Express, which is by the folks that wrote Gabby. It's by PE International, but it's a plugin to SolidWorks, which is a 3D modeling program, a CAD program. And so it has a great user interface. It's very simple, but it doesn't show you very much data. It shows you, if I remember, actually I have a screenshot in a second. So like this is a screenshot of SEMA Pro. You can see not super user friendly. And this is a screenshot of Sustainable Minds. Much easier to find your way around, and it has much more of a wizard sort of method of typing data in. And this is Greenfly, and this is Sustainability Express. So nice simple interface, but it only tells you carbon footprint, air acidification, water eutrophication, and then total energy consumed. And again, energy is not a very useful measure because the impacts of that vary a lot depending on whether the energy was from wind power, let's say, or solar power versus whether it was from a coal plant. But certainly the carbon footprint and water eutrophication and acid rain or air acidification are useful. And one other limitation on Sustainability Express right now is that it can only do parts, not assemblies. But I'm sure that they'll deal with that in time because it was just released this past year, so it's very new. And so once you do the analysis, you get a bunch of charts and graphs and stuff, and then you need to make sense of things. I'm going to get another drink here. So this is a typical graph that you would get from Sustainable Minds, and it's showing you single score impacts for all the different components in a particular product. So this big blue bar here is that is the electricity use of the product during its life, and this bar here is the process of rolling steel, or sorry, milling steel. So that's the second one here. And this one here is the raw material of copper, so mining copper out of the ground. And this next one here is mining steel out of the ground. And so you can see that these four impacts here are the vast majority of the impacts of your product. And so before you even start bothering about the, let's say, transportation or the packaging, the craft paper, or other things, don't even worry about that until you have fixed these big impacts here. And obviously electricity use during the life of the product is the biggest one that you need to worry about. And next up, there we go. So that hairdryer that we were looking at before, this is that same graph that I showed you earlier. Once again, we have these sort of three big bars, and the colors in these bars that I told you not to worry about earlier, these are the various different kinds of impacts. So this is the difference between SEMA Pro output and a Sustainable Minds output, is that this just basically gives you more detailed information. So the green color here is mineral depletion in the manufacturing, and the sort of oily gray-green color is fossil fuel use. And the yellow is air pollution. I believe that's respiratory inorganics. Yeah. And etc. Another thing that you can get for output is called a Sankey diagram, where it's basically just a bubble chart of the different processes with the arrows in different thicknesses showing how big the impacts are. So this is that same hairdryer, and this here is electricity use. You can see it dominates, whereas this here is the manufacturing, and so all the stuff under that is part of the manufacturing. And it's not even showing a bunch of the earlier bubbles. You can see that there are lines going to nowhere, just because there's such a small part of the impact that it's not even bothering to show them. Now, sensitivity analysis, remember how I was saying that you need to make assumptions along the way. It's just inevitable. And so the question is, how much do those assumptions matter? Because sometimes they matter a great deal, and the results of your analysis can hinge on the assumptions that you make. So this is that same graph that I showed you earlier of the hairdryer, where all this stuff here is the manufacturing, and this is the transport, and this is the electricity use. And so this would imply that since electricity is such a big problem, if you even improve that by 10 or 20%, that would be equivalent to improving the manufacturing by 100%, just because it's so much bigger. So that should really be your first priority. But this is assuming that the hairdryer is used for 10 minutes a day, every day, for 5 years. Now, that seems like an awful lot of use. Now, that was what the manufacturer told me is what they expected average use to be. It seems crazy high to me, but I don't use hair dryers. I'm not their target customer. So I said, okay, well, how big of a difference does that make? So what if I instead assume that it's just used for 2 minutes a day for 5 years? And then this is what you get. And so you can see that electricity is still the dominant impact. It's still the tallest bar, but it's not that much different than the manufacturing. And so now it makes more sense to say, all right, let's improve the manufacturing here. And finally, scenario modeling. This is another really useful thing that LCA can do if you're in the product development stages or the product redevelopment stages, and you're saying, we want to make a better hairdryer or a better whatever it is that you do. You can run different scenarios and see which path to go down, which one is going to give you the best bang for the buck. So, for instance, with the hairdryer again, landfill is not a very significant part of the impact here. But what if we recycle the hairdryer? Well, gosh, that is actually a significant improvement. That takes off a lot of the impact of the manufacturing. So maybe recycling would be a good thing. Although it's still a smaller impact than electricity use. So if we're really going to make a difference, let's shoot for the electricity use. This is a different product done in Sustainable Minds, where one scenario is let's use low impact materials for the manufacture of that product. And the other scenario is let's use the same exact materials, but let's make it more energy efficient. And as you can see, the energy efficient one wins because it has the lower impacts. And so you don't need to go through the whole product development process on that alternative material version. You don't need to do the prototyping and the user testing and measurement and stuff like that, because you can see after just a few minutes in the software that energy use is going to get you bigger impacts. And this was a really interesting one. So the hairdryer company had already developed an alternative model that they were hoping would be a lot better because it used 35% less plastic in the case. And so it was 35% lighter. And that's a big difference. You know, it's a pretty significant engineering improvement to cut more than a third of the material out of your product. I mean, that's really great. The trouble was, since the plastic use, since the material use was not their biggest impact, that didn't end up making a big change. In fact, of the two bars that you'll see here, you'll notice that the one on the left, the higher bar, is actually the lighter hairdryer, whereas the one on the right is the standard hairdryer. And so you might ask, how come this one is actually higher than that one? Well, it turns out because they were adding a feature to this one. There was an electronic component that was in there that was not in the standard one, and electronics often have a much higher impact than just a little chunk of plastic, because the semiconductor processes they're more energy intensive, they're more toxin intensive, et cetera, et cetera. And so they have a much higher impact per gram of material or per pound of material than some more polycarbonate or polypropylene or something. This is just a sketch of sort of the process of doing LCA. And it's just to show you that it's not necessarily a linear process like I sort of pulled out for you before in all those bullet points where you do the boundaries and then you do the lifetime estimate and functional unit, and then you gather all the data on the materials, et cetera, et cetera, et cetera. It's not always that linear a process, because as you go through things, when you're making your assumptions, you'll go through and you'll do the analysis and you'll find, wow, that seems sort of like a suspiciously big impact. Let's do some sensitivity analysis. Let's see what happens if I go back to the beginning and change that analysis and do things all over again. Or maybe through the course of the analysis, you'll find, wow, the functional unit that I chose, cups of coffee, was actually not good because it's not quite a fair comparison, et cetera, and then you'll readjust that, redo the analysis, and so it can be a back and forth process. But that is it for the lecture, and so what questions do you guys have? Okay, there's one here. Are LCAs available for public consumption? And the answer is yes, sometimes. Basically, there are a lot of LCAs that are published on the web, and sometimes a good Google search can turn up analyses that people have done on whatever, paper bags versus plastic bags is one that there are a few out there on, and some that contradict each other, interestingly. Remember, physics in the 1700s. And then for the Ocala guide, like I showed you, there are those tables in the back that show you data for different materials and different processes, and those are generally industry average numbers. In the case of Ocala, they're American industry average numbers. In SEMA Pro, if you're looking at a lot of data in the EcoInvent database, most of the data in there is European manufacturing data. They're starting to come out with some data from China or other parts of Asia. But we need a lot more of that. There's really not very much these days. And so the answer is yes, basically, but it can sometimes be hard to find, and you need to know how to judge the credibility of the data that you're looking at. Okay, and there's another question. What's your opinion of the newly forming Walmart labeling of products? That's a good question. They are definitely making an honest attempt. And I think it's a great step forward. I mean, it is a fundamentally hard problem. I would prefer something that is more life cycle analysis based or life cycle assessment based, whereas theirs is more of a it's more like the LEED rating system for buildings, where they have a bunch of different categories, and they give you points based on how you score in that category. And so that doesn't necessarily adjust for, let's say, one product is going to be really energy intensive just by means of that category of product. Like if you're comparing, say, computers and Barbie dolls, okay? Like Barbie dolls, they don't use any electricity, and so that's not an important part of their impact, whereas for computers it is. And if you were using an LCA-based analysis, then you would get a more fair measurement of which components are more important for which product type, rather than the category-based system. But I do think that it's a pretty good-looking system, at least in the beginning. All right, other questions?
Hey, thanks so much, Jeremy. It does. I had a couple offline questions to ask you, but it looks like we had another question coming in from the audience asking if any of the web-based LCA programs are appropriate for compostable bioresin cutlery, which tends to be made of PLA or polylactic acid. The boundaries starting from materials and manufacture through use to disposal by composting. Comparison would be with polystyrene cutlery going to the landfill. Do you know if there's any LCAs available for those products specifically?
I know that people have done LCAs on that kind of stuff. So for that, it's actually it wouldn't be a question of whether the online programs are better than the offline programs. It would just be a question of, do they have the data for that particular material? And I believe that the EcoInvent database does have data for PLA, so I believe that both Sustainable Minds and any desktop program that uses the EcoInvent database, like SEMA Pro or Gabby or other ones, would be able to have that data. Yeah, so it just depends on which database you're using, but I think so. Oh, and there's a question of what my email address is, basically. So yeah, if you guys want to contact me, my email address is jer@faludidesign.com. So that's JER@Faludi, my last name, design.com. Also, if you just Google Jeremy Faludi, you'll pull me up very quickly.
Not a lot of other Jeremy Faludis out there, huh?
Yeah, not so much.
I have an offline question here that has to do with something a little more towards the beginning of your presentation when you were talking about a specific LCA tool using millipoints as the measurement scale. And the question is really related to how we can compare LCAs that essentially use a different scale. Is anyone working in that area where if you use a Prey tool or model and someone else is using a Sustainable Minds tool and they're using two different scales, is there some sort of apples to oranges way to compare the two outcomes?
Right, sort of. Although, so first, let me clarify again that it wouldn't matter if you're using Sustainable Minds versus SEMA Pro. You could use the same methodology in both programs. You can use Tracy in both Sustainable Minds and SEMA Pro. Although I think Tracy is the only method that Sustainable Minds uses. I don't think you can choose to use like eco indicator method or whatnot. But so the way that you would translate between an analysis done in the eco indicator method versus the Tracy method is basically by going back into the data. So each of these methods is based on actual direct measurements. So, for instance, when Tracy is evaluating the respiratory inorganics and organics, they're looking at actually how many grams of 100 different chemicals are output by the, say, emissions of a coal power plant or the emissions of the steel plant that's manufacturing the steel. And those are all going to be in a database somewhere. And so Tracy and Eco Indicator are looking at that same data. They're both getting the same number of grams of this chemical and the same or milligrams of that chemical and this chemical and whatnot. But then they're just taking that data and they're weighing it differently to get their different scores, basically. And so the best way to translate between them is rather than trying to go directly from Eco Indicator to Tracy is to go back to the data. And if you have one of these software programs, then that's very easy to do, because everything is just entered by, you've got so many pounds of polycarbonate in your product, so many pounds of steel, circuit board, et cetera, et cetera, et cetera. And then you can just click a button to say, analyze this using Eco Indicator or analyze this using Tracy. You can just flip back and forth at a moment's notice. But if you're sitting down with, say, two published analyses where you don't get that data, you just get the results that they got, then that is a trickier thing. And I don't know that I could give you good advice for trying to translate that, precisely because they weigh things differently. And interestingly, part of the ISO 14040 standard is that when you're comparing two different products, like two different hair dryers, or comparing a hair dryer versus a car, or comparing a bicycle commute versus a car commute, then you're actually not allowed to roll all the different kinds of impacts together into a single score. You have to compare each kind of impact separately. So you can't do the sort of analyses that I was showing a minute ago, like this, where you just have this hairdryer versus that hairdryer. You have to show, okay, the carcinogens in this hairdryer versus the carcinogens in that hairdryer, and the climate change in this hairdryer versus the climate change in that hairdryer, and boom, 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 boom for all the different impacts. So I hope that answers your question.
No, that absolutely answers the question. Thank you. I think, sort of stepping on top of that, we're talking a lot about the Eco Indicator and the Tracy methodologies that these tools are using. I think you were saying earlier that the Eco Indicator methodology is the most popular, but that you just mentioned Sustainable Minds using Tracy. Are there different methodologies that are better for different industries or products or services, or are none of them are really industry specific, and they're just a little bit different, and it's really more oriented around your preferences? Or what's sort of the big differentiators between them, and are there any better applications for each?
That's a good question. Each system certainly wants to be universal. It tries to be fair and unbiased, and tries to do its best to measure the impacts, because the people doing the analyses, they don't really care what the industry is that is initiating the analysis. They care about the impacts on the world. So these are environmental scientists that are trying to measure, what are the impacts of water pollution, air pollution, toxicity, etc. And so they don't really care whether the product is in the entertainment industry, or whether it's a building or what. And in fact, they want to make it as universal as possible so that you can really make as intelligent decisions as possible. Now, I do happen to know that the architecture industry in the U.S. tends to use Athena and bees. I honestly don't know why they prefer that to, say, the Eco Indicator methodology or the Tracy methodology. So in terms of choosing one standard versus the other, like, the reason that I tend to prefer Eco Indicator is because it measures a couple things that Tracy doesn't. It measures mineral depletion, and it measures some of the bulk resource use, like sand and gravel, in its land use calculator, which doesn't sound that important, but actually, if you look at the numbers of materials that you use as an average person in America, somewhere around 2/3 of your material use is sand and gravel. It's because of all the material used for concrete in roads, and also buildings as well. But it's a lot of material use. And yeah, maybe not as damaging to the environment as some other things, but still worth measuring. But I do wish that there were a system that measured water use, and that had some kind of normalization for, whether that water was used in Phoenix or Portland, Oregon, or Seattle, etc. Yeah, and people are constantly coming up with new methodologies. Actually, Scientific Certification Systems is coming up with a new methodology that is more comprehensive than anything else that I've seen out there. And I'm sort of pretty excited about it. I don't know if it'll become a new industry standard or not. Time will tell. But it's definitely an evolving science.
Pretty amazing statistic you just gave on sand and gravel being 2/3 of our materials use. I had a follow-up question to that regarding boundaries, but I'd like you to maybe follow up with the online question from one of our attendees about if there's any available data on the impact of worldwide shipping, specifically from Southeast Asia and China, versus trucking across North America. For example, having a manufacturing facility in China and container shipping from there versus having a manufacturing facility in Mexico, southern Mexico, and trucking up from there. Is there of any data available on that?
Yeah, actually, there's tons of data on stuff like that, and any decent life cycle analysis or life cycle assessment program or tool will have that data in it. So yes, that's very easy data to get, and it's all over the place. And just to give you a rough benchmark, sort of a rule of thumb, the ecological impacts of shipping by boat and by large container ship and by train are roughly equal, but the impacts of shipping things by truck over land are about 10 times that of shipping by container ship per mile, and shipping by air is about twice shipping by road, so about 20 times worse than shipping by container ship. And so yeah, in fact, it could very easily be more environmentally friendly to get a product made in China and shipped here if the end user is in San Francisco, where I happen to live, as opposed to getting the product manufactured in southern Mexico and trucked all the way up, just because the 10 times factor makes a very big difference.
Interesting, but it may be that it's a little more efficient to actually truck to, say, the East Coast from southern Mexico if it adds enough miles to the shipping lane to sort of up the overall floor
right.
of the shipping from Southeast Asia. I would imagine logistical is
right,
most people is one of those low-hanging fruits that people want to grab almost instantly when they start on LCAs, looking at their product life cycles. That logistics is one of those things they want to grab right away.
Yeah, and often another surprising thing that you'll find is that transportation is usually not a very big component of the life cycle impact of a product. I mean, a lot of people have been getting very up in arms about local manufacturing and local food and stuff like that in the last few years. But really, if you look at the numbers, transportation is often a very small part of the impact of a product compared to the manufacturing of the product or the energy use during the product's lifetime.
That's really interesting. Every answer you've come out with this extremely interesting statistic that challenges some of the common thinking today about product life cycles. I'd like to go back to that one actually that you said a couple questions ago about materials use and sand and gravel being about 2/3 of our materials use, as long as you look at a pretty wide boundary for an LCA. And I wanted to discuss boundaries really briefly. Because you were mentioning the more precise that you draw your boundaries, the more centralized you keep them, sort of the more accurate and the more certain you can be about the accuracy and the consistency of your LCA. I'd like you to, if you could, sort of compare and contrast that with casting an extremely wide net and really having a boundary that tries to incorporate all aspects of whatever you're doing your assessment on. In terms of possibly those smaller boundaries can create maybe an incomplete analysis, whereas those wider boundaries, while you may not be able to be as certain about all the data and the consistency of it, it at least tries to sort of do a full front-to-back analysis. What's sort of the best approach, if there is a best approach, on how to define your boundaries?
Yeah, I don't know. I think that you actually summed it up quite well there. Just with what you said, that it's a balancing act between sort of precision and completeness. And there was the example that I gave before with the cell phone. Do you include just the cell phone or the cell phone towers? Or another example of where the boundaries would be too close in could be with the hairdryer, because remember when I was looking at the electricity use during the product's life, I had to estimate how much usage it got over the life of the product. Whether it's 10 minutes a day or 2 minutes a day. And I don't know those numbers. And in fact, the manufacturer did not even know those numbers. They had not done extensive studies on how much their product is used. So they didn't know the answer to that. And so that's a big guess, obviously. But if I had drawn the boundaries closer in and said, okay, well, so that's really uncertain. There's there's assumptions going on there. So I'm gonna leave that outside of the analysis. I'm just going to look at the manufacturing impacts of the product. Now, you could certainly say that. You can draw your boundary there and say that this is an LCA of the manufacturing of a hairdryer, and it doesn't include the usage or the end of life, and that's fine. But it's not going to be a very useful analysis because, as you saw, that stuff that you were leaving out, the electricity use, is in fact the biggest part of the product's impact over its life. So that would be a case where you do want to draw the boundaries farther out, even though you're doing more guesswork and it's messier. But that's such an important part of the product's life cycle that you really need to.
I would imagine sort of product externalities are something that you have to make a bunch of assumptions on that people would probably prefer to leave out of some LCAs than incorporate many times, because it makes their process a lot more difficult. But then again, bringing it back, like you said, can create sort of that incomplete analysis, and you're leaving out sort of the largest piece of that LCA. And that leads me to ask your opinion on a term I've heard being thrown around lately, which is good enough LCA. And I feel like that is sort of an approach that just assumes that maybe 80% of the results and the knowledge come really from 40% of the effort and that last 60% of effort's only getting you marginal benefit, 20% of the results. And I'm wondering if you think that that sort of good enough LCA approach is good for people trying to get into LCA, possibly conduct their first or bring it into their company. Does it work well, or does it sort of hinder the adoption of a full-fledged LCA, which could be much more beneficial in the long run?
Yeah, no, I think that's a great idea. The only trick is you have to do enough of the analysis to know what matters and what doesn't matter. Because, like, for instance, with the hair dryer that I was showing before, where there was the lighter one that actually ended up having a higher impact than the previous one. That was just because of one little component, one small electronic component. And so if you were trying to do, if you were just saying, oh, we'll, in our bill of materials here, in our analysis, we're only going to include the, the heaviest dozen things, and all the smaller components we're not going to bother entering in. Well, guess what? Some of your smallest components can actually have some of your biggest impacts sometimes. And so that would be the caveat, I would say. That would be the trick with doing a good enough LCA, is you need to, basically you need to put in enough of the data to get that useful result. And particularly if you're new to LCA, you may not know what the important things are and what the unimportant things are.
Great. I know we are just about out of time, and I want to squeeze in one more question for you, and that's related to the software piece you were discussing earlier. And there's been, I guess, I don't want to say an advent, but certainly Sustainable Minds is offering their tool online now. There's a bunch of, localized LCA programs you can run locally on your machine, and now there's some web-based products coming out as well. I'm wondering where you see the future of LCA going. Is it going to be local machines? Is it going to be web-based? Or is it going to be really going to be migrating into the design tools like the plugin for that CAD program, so that you can actually get some analysis and some assessment on products as you're designing it, and do it as you go? Do you see one of those areas really growing a lot faster and dominating?
Well, I certainly want to see a lot more analysis built into design tools, like Sustainability Express is. In terms of desktop-based versus web-based, I don't really think it matters. Web-based can be more convenient just because it's automatically cross-platform, and it can be easier to share your results amongst colleagues, rather than having to export the results to some format, to PDFs or images or Excel spreadsheets or something like that. You can just give the person the URL and your password, and they can go in and see the full thing. And so that's the kind of the only way in which it really matters whether something is desktop-based versus web-based. And that's kind of true for any program, whether it be Illustrator or Photoshop or Excel or whatever. But yeah, I think that the big difference in terms of convenience and usability will be when these things get built into CAD programs more often, and when it can do more than just analyze a part, it can analyze a full assembly as well. That's when it will become much, much easier. But there are also advantages for not doing things that way as well, because if you're in the conceptual design phase, you're just in the early stages, and you haven't even made a model. You don't even know what the product will look like yet, necessarily. But you can make sort of rough guesses. You can say, oh yeah, it'll probably be about, whatever, half a pound of polycard in the case, and there'll be a circuit board that'll, probably be about yay big or so. And you can just make these assumptions, boom, 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 without having to go through all the time and effort of modeling them up in a CAD program, which takes a good deal of time all by itself. So I certainly don't think that should be the only place for LCA software to live. It'll be a great place for some LCA software to live, but they'll also be a very useful place for the standalone products as well.
Great. Thanks so much for being here today, Jeremy, and sharing your knowledge of LCA with us all. I really appreciate it.
Sure.